All right, so yesterday, or actually Monday, we talked about preparation of ethers. We said in industry, you can just take an alcohol, treat it with strong acid. Those two equivalents of alcohol will actually combine together to make a symmetric ether. However, this is pretty dang limited. It's used for only symmetric ethers that are relatively small and unfunctionalized. The Williamson ether synthesis was our fancy SN2 route, where we said you can take any alcohol, treat it with a strong base like an alkali metal or sodium hydride, make your alkoxide, which is now a good nucleophile. That can then do SN2 chemistry with methyl or primary alkyl halides, and you can end up with any sort of ether that you want out of this. There's actually one other one that we didn't have time to cover the other day. So let's jump into the new one. And this can be made using alkoxymercuration demercuration. And let's do a little bit of review from chapter 9. If you remember in chapter 9, we could do this reaction with any alkene. And we had two reagents. In fact, I'm going to show it like this. And you could get your alcohol to install on your more substituted side. And what was the purpose of these reagents again? Avoid rearrangement, right? And what were the reagents? I guess we're kind of jumping the gun there. Yep, HgOAC2, so mercuric acetate. All right. And if you remember, there was one other important reagent we needed specifically to install the alcohol. Water, right? So when we do this, whoops, we'd say H2O, and we needed that water to install the alcohol group. And then in step 2, how did we do the demercuration? NaBH4. Same reducing agent we saw for alcohols. All right, you can do this for ethers as well. And let's use the same starting material. However, this time, we're going to try to install an OR group rather than an OH group. So now that R is some sort of carbon chain. Just like before, we're going to use mercuric acetate. However, instead of water, what do you think we're going to use? Yeah, just some kind of alcohol, right? So just like before, we want to be careful what we select. If we use water, we're going to get an OH group. If we use an alcohol, we're going to end up with an ether. And just like before, we're going to reduce using sodium borohydride. So this is one variation on what we've previously seen, but it's not super common because it's not very green, right? Most people would avoid this because of the mercury. If you're a little rusty on the mechanism, go back to chapter 9. I'm not going to redo the whole mechanism again because it's identical to what we've seen previously. All right, so there's luckily only one reaction of simple ethers we need to learn, and it's a relatively uncommon one, but I'll show you it anyways. And I'll go ahead and make a bifunctionalized ether. Some people get confused when they see R and R prime. That just means that R groups are different from one another. And the only reaction we really have where we can do anything with these ethers is to treat it with a wickedly strong acid, and I'll call that HX. And in this case, it won't even work with hydrochloric acid. It will only work with hydrobromic acid or hydroiodic acid. So I'll write X equals Br or I. And what do you think the first step's going to be if you treat this with a wickedly strong acid? Protonation, right? All right. So I'll go with my orange pen. We'll steal a proton. We know acid-base chemistry is going to outcompete everything else. And then we've got this leaving group, our conjugate base X minus. At this point, we could say, hey, this is a good leaving group. Just like we saw with alcohols, the only way to make them into good, or one of the ways of making them into a good leaving group is to protonate them. Now this can attack the backside and kick this off as a leaving group. And now we formed a new halogen-carbon bond with one side of the molecule and split it into two. Does that make sense? All right. If we've got more acid around, which usually this is done in excess, we can keep on reacting. And just like before, this alcohol will quickly get protonated by the acid. I'm just going to include everything here for the sake of being thorough. And just like before, we've made this a good leaving group, which means this halogen can attack this backside and kick this off as water, which means your final product from this reaction will essentially be a split ether, where you now have two halogens coming off of each side where there was once an oxygen. And you must also have water as your byproduct. So this is a way of splitting ethers. One thing I will say is it's not super common. It's not synthetically useful because acids that strong tend to do a lot of other chemistry besides just splitting ethers. So it's not super common, but it is one reaction you could theoretically do with ethers. Make sense? Normally, if we want to make an alkyl halide, we'll do things like normal substitution chemistry, or we'll do radical halogenation. This isn't super common. All right. Now we got to switch gears into epoxides. We said normal ethers are relatively inert, unreactive, not that interesting. They're usually used as solvents or just substituents coming off a parent chain. Epoxides, on the other hand, are super duper reactive. So let's do a little review. Let's say I've got this alkene, and I want to make this into an epoxide. I'm going to show stereochemistry too. What reagent do I need? I'm going to move this. MCPBA, right? For bonus points, does anybody remember what MCPBA stands for? Metachloroperoxybenzoic acid. It just rolls off the tongue. All right, so let's draw that. Oops, this should be a chlorine. This is metachloroperoxybenzoic acid, aka MCPBA. You can use this to install that oxygen, or you can use another peroxy acid. You may see this one commonly on sapling. However, our textbook tends to favor MCPBA. And this is just called peroxyacetic acid. The key feature in both of these, though, is this oxygen-oxygen single bond in that carboxylic acid side of the molecule. Does that make sense? That's why it's called a peroxy acid, is it has that extra oxygen. Okay, so these epoxides are incredibly versatile and useful. However, there is one other way to make them. This method is the most common. However, you can make them via a halohydrin reaction. And we haven't quite seen this yet. However, let's review our halohydrin reaction. What reagents do we need to install a bromine and an alcohol across the double bond? Yeah, bromine and water, right? If all we have is bromine, then we get 2 halogens, but if we have water around, you'll get a halogen and an alcohol. Okay? And second question, is it going to be syn or anti-addition? Anti, right? So we'll have a bromine on one side, an alcohol on the other, and in this case, you'd end up with a mixture of enantiomers out of this, right? So that's our classic halohydrin reaction. But what was found is if you treat this with sodium hydroxide, I'll just show hydroxide here, you can do acid-base chemistry. So let me actually show this bond. If you do acid-base chemistry, you can quickly steal this proton. Now this oxygen has a negative charge. It's an alkoxide. You've got this bromine over here, and just like before, this would be a mixture of enantiomers. And it's weird to think about, but this oxygen right here is a good nucleophile. And over here, we've got a good leaving group. So this can actually do what's called an intramolecular SN2 reaction, meaning it'll attack itself. So this oxygen will quickly clamp down, attack that carbon, kick off this leaving group through an intramolecular SN2 reaction. And when you do this, you'll end up with your oxygen as a bridge, and so this would be your epoxide plus your enantiomer. So you could show those both as dashes or wedges, doesn't really matter, and you'd end up with your epoxide. For your problem of the day, I gave you guys this sort of reaction. However, it's involved in a cyclohexane ring. One thing I will say is you may have to go back and review chair structures. I actually did that on purpose so you guys don't forget chair structures. And think about the intramolecular SN2 and which chair structure would be more stable, one versus the other. This would be a good one for breaking out model kits and physically seeing the chair structure too. All right, so let's take a look at some of these reactions. And in particular, I want to focus on stereochemistry. Okay, so let's say I've got this compound, and I treat it with MCPBA. What epoxide or epoxides will I get out? It's a little bit weird to think about, but I always start out by just drawing my simple epoxide and then appending substituents on as needed. So I'll show you guys what I mean by this. So we know our epoxide looks like this. We know each corner of that triangle must also have 2 substituents coming off of it. One will be a wedge, one will be a dash. And then the question is, all right, what goes on what position? And the way I like to remember this is I circle one side, and I'd say these will be cis to one another, meaning on the same side, right? All right, that means they both must be dashes or they both must be wedges, right? So for example, I'll say, all right, this methyl group right here, I'll put as a dash in the back, so I'll just write CH3. And on the other side, that same dash must also have an ethyl, so I'll just abbreviate that ET. Does that make sense? All right, and then on the front, I'd say, all right, we know we must have an assumed hydrogen right here, and same thing here, these must be cis to one another. All right, so given our framework that we have now, will the cyclohexane be on the left or right-hand side? Left, right? Because it's on the same carbon that has that methyl group. So I'd say, all right, that cyclohexane's got to be coming forward, and the hydrogen's got to be on that same side, so it would look like this. The reality is that this has stereo centers. We can't control whether or not that oxygen gets installed on the top face or the bottom face, so let's show the other one. Let me clean this up a bit. There we go. Not the greatest drawing I've ever done, but you get the idea. The oxygen can either be the top bridge or the bottom bridge. And what's the relationship between these? They're enantiomers, right? They're mirror images of one another, but they're not superimposable. Alternatively, what you can do is just draw one of them and write plus EN, right? We have zero control over which one we're making when we use MCPBA as our reagent. That's a pretty big problem because this is very useful in organic synthesis. And so chemists tried very, very hard to figure out how to install an oxygen on one side of an alkene and not the other. And I'll show you guys this one, although it is very advanced. And this is called enantioselective epoxidation. This was the 2001 Nobel Prize to a handful of chemists that worked on them. This, one of whom was Barry Sharpless, same guy who did the click chemistry that we talked about in our lab previously. And so what he found was that some types of alcohols, you can actually favor one enantiomer over the other. And I'll show you the alcohols that work. What sort of carbon is this in relation to the double bond? It's allylic, right? So this is an example of an allylic alcohol. And what he found was you could selectively get one enantiomer over the other by changing your reagents. You could use this peroxide with the tert-butyl group, and then a titanium catalyst with isopropyl groups on it. And then he used diethyl tartrate. The reason he used diethyl tartrate is you can get one enantiomer over the other. So you can actually order a pure enantiomer of it. And by doing that, it basically transfers its own chirality to the epoxide. And what he found was when you do this, you can make an epoxide that is dang near enantiomerically pure, where it only installs on that top face, for example. And then he found out that if you change these conditions a little bit and use the other enantiomer, you get the other epoxide. So he used the other enantiomer of diethyl tartrate. And just like I said, we'd get the mirror image of this. This was revolutionary for natural product synthesis and allowed chemists to do a lot more interesting chemistry than they could have before. They didn't take that immediate 50% hit every time they made an epoxide. They were able to make it in almost 99% enantiomeric excess or higher. So this isn't something I'm necessarily going to expect you to know the reagents on, but I just show it to you because occasionally they'll ask questions on sapling or even the ACS exam where they throw these weird reagents at you. But this is called the Sharpless epoxidation. All right, so now let's take a look at reactions we can do with these epoxides. This is where it gets fun, believe it or not. I know you guys think it can't get any more fun than this. No, he is a legend in chemistry, or in the chemistry community, so I think people just automatically called it after him. Interesting story about lab safety, completely unrelated. So you know how I always hound you guys to wear lab goggles? Apparently the story was he went into his own research lab while his graduate students were working, and his graduate students were cooling something. I think it was in liquid nitrogen, and there was actually condensed gas in there. He didn't know what they were doing. He just came in and was poking around, didn't put on safety goggles, pulled it out of the cold bath, was looking at it, and it shattered the glass tube straight in his eye. So he's blind in one eye because he didn't wear his safety goggles. That's why I hound you guys. So something to think about when I'm hounding you about wearing safety goggles, that even Nobel laureates will lose an eye. All right, so let's go ahead and make our epoxide, and then we'll look at the reactions we can do with these epoxides. All right, so MCPBA will make an epoxide. Like I said, I make my epoxide ring, and then I put on my stereo centers. In this case, we've got two methyl groups on one side. Do we have to worry about enantiomers here? No, we don't even have a stereo center in here, so we're fine. And in the next step, what you can do that we've seen previously is treat this with strong acid. And like we saw in chapter 9, you can protonate that oxygen. This oxygen now has a positive charge. And then if you remember, I said if you've got a nucleophile, it's going to favor one carbon over the other. And which carbon will it favor attacking? The more substituted one, right? So in this case, it's going to attack here, slingshot this open. And in fact, this was the way we saw for making anti-diols. So if your nucleophile is water, then that OH will be anti to the alcohol that got slingshotted open, right? The other thing is this is kind of half the story. So I'll explain why. If we look at this carbon, is that primary, secondary, or tertiary? Primary. It's only attached to one other carbon. So this is a primary carbon. Over here, that means that carbon must be what? Tertiary. Okay, so let's make a note. With acid-catalyzed ring openings, your nucleophile prefers to attack tertiary carbons if available. And does anybody remember why that is? Going back to chapter 9. The reason for this has to do with the transition state. So I'm going to actually draw the transition state over here. And if you think about it, we're forming a new nucleophile bond to this lower carbon. We're breaking this bond over here. One methyl group is going out like this. One methyl group is going out like that. We've got a hydrogen still off that oxygen. And when we do this, the nucleophile is essentially going to carry a partial negative charge. And when we look at this overall reaction, the goal is to stabilize the transition state. So when we look at this carbon is more stable because it's got more substitution coming off of it. What do we call that when things are stabilized due to increasing substitution? It's not conjugation. You guys remember? Hyperconjugation, right? What stabilizes carbocations? Hyperconjugation, increasing substitution, right? So that carbon is stabilized due to hyperconjugation. And we know that tertiary carbons are a heck of a lot more stable than primary or secondary carbons, back from our chapter where we covered carbocations, right? All right, so that's the story with tertiary carbons. However, we do have a weird example.
Hey, Joe.
Yep.
Can you go over again, like I think you talked about this before, can you go over again what hyperconjugation means?
Yeah, so hyperconjugation means you've got adjacent sp3 hybridized carbons, right? And we said that they don't have true resonance, but those sp3 lobes will actually help stabilize any carbocations by dumping some electron density into that empty p orbital. And when we're going through this transition state, we're essentially going through a trigonal planar transition state, which means it's sp2-like. And so that helps stabilize it. Yep. All right, so let's take a look at a weird example. What happens if we don't have a tertiary carbon? So in this example, I'm going to treat this with MCPBA. We're going to make an epoxide. This time we do have to worry about enantiomers because we know we have got a hydrogen here, so I'll just write plus En. Same thing, we're going to treat this with acid. So this oxygen will now have a positive charge. Methyl group's still going to be a wedge. Hydrogen that's assumed will be a dash. And now we need to think about our nucleophile attacking. In this case, we've got a primary carbon here, and we've got a secondary carbon right here. If you don't have a tertiary carbon available, it will actually prefer to go after the less substituted carbon. Okay, so let's make a note of this. So under acidic conditions, if no tertiary carbon is available, your nucleophile will attack the less substituted side. And so then the question is why? So let's go back up and look at the first one. We said up here, at least with our transition state, that it was explained through this electronic stabilization, right? So electronically, this had the lowest activation energy. If we look down here, we're saying, all right, it prefers to go after the less substituted side. Why do you think that's favored in this case? It's not electronically, sterically, right? So in this case, the nucleophile just has an easier time approaching the other side. Really, this comes down to the fact that the secondary carbons really aren't that electronically stabilized. That means that sterics actually wins out over electronics. It's this weird duality in organic chemistry where you're looking at electronics and sterics sometimes. Sometimes sterics wins out, sometimes electronics wins out. All right. It can affect it. However, usually if you've got a bulky nucleophile, it will favor the less substituted side in general. These aren't absolute rules, they're just general trends. That's a good question. All right, and then we've got one more example. These first two that we looked at were all under acidic conditions. However, you actually don't need acid around in all of these examples. And luckily, this one's a little bit easier. So let's take a look at same example. We'll use MCPBA. We'll make our epoxide. Got one methyl group here, the other one going back like that. In this case, we need a strong nucleophile. That means that this nucleophile must be negatively charged in order to be strong, or in some cases is sulfur. And in this case, your nucleophile will always favor the less substituted side. And then last but not least, we must have some sort of proton transfer. I didn't show the proton transfers above, but they would also have proton transfers where needed. And you would make your ring-opened epoxide. So let's make a note. Under basic conditions, always attack your more or your less substituted side. Excuse me. So it does get a little confusing remembering these rules. In general, remember that under acidic conditions, you attack the tertiary carbon. If available, under basic conditions and all other conditions, go after the less substituted carbon. All right, so I don't know if we'll have enough time to do all of this, but I did want to show you all of the potential routes you can do. So I'll do under acidic conditions up here. Or actually, sorry, I'll do non-acidic. I'm going to just take a general. Oh, yeah, sorry.
How do you know if it's acidic, non-acidic, or basic? Is it just going to say?
So you'll know it's under basic conditions when you see your nucleophile in general has a negative charge. Under acidic conditions, you're adding in some sort of catalytic acid like sulfuric acid or tosylic acid or phosphoric acid, something like that. Yeah. So we can actually convert this to a thiol. And what reagents do you think we would need to convert this to a thiol under non-acidic conditions? Just need sulfur with the negative charge, right? We know we need a strong nucleophile. So I would use this because we know the sodium will have a positive charge, the sulfur will have a negative charge. And then in step 2, we need to protonate it. So I'll just write, all right, H2O would do the job, and we can install this sulfur functional group. Alternatively, we can install a nitrile. However, this one requires a little bit more lab safety. In this case, we would need a strong nucleophile. So in this case, most people would use potassium cyanide, super duper toxic, not the most environmentally friendly reagent, followed by H2O. And just like this one, we swapped out this sulfur onto the epoxide. This time, your cyanide is actually going to attach directly on. Another cool one you can do is make an ether directly from these. And what reagents do you think we need to make an ether? Yeah, an alkoxide in particular. If we had hydroxide, we get an antidiol. So in this case, I'll say NaOR. So that could be a methoxide maybe, ethoxide, you name it, it could add in. And then step 2 would be water. Another cool thing you can do is you can actually add in a carbon group. And how can we make a carbon supernucleophilic? You can't just throw methane at it, right? What have we seen where carbon acts as a strong nucleophile? Yeah, the Grignard reagent. And then treat that with water, and you can actually install a carbon group onto an epoxide. All right, last but not least, before I let you head out, so you can actually ring open these with a hydrogen. All right, how do we turn a hydrogen into a nucleophile? It can't be a proton. What do you guys think? If it's not a proton, it must be a hydride. What reagents do we know of that have hydrides on them? NaH, that's a good base. If you remember, I said that's not a good nucleophilic source, though, because it's insoluble. What's another one we've seen with hydride? NaBH4 or lithium aluminum hydride. In fact, most people for this one would use lithium aluminum hydride. That will install the hydrogen as a hydride. And then last but not least, you quench this with water. So that's why epoxides are so versatile, is we can really quickly change an epoxide into a new functional group. All right, tomorrow when we come in, we'll finish up talking about acidic conditions, but you can imagine it's pretty dang similar, and then we'll do some practice problems and finish up with diols.